Think of the most profound silence you have ever experienced. Not the quiet of a still night or the hush of an empty room, but a true, absolute silence, one so deep it feels less like an absence of sound and more like a presence. Now magnify that silence across an infinite, airless expanse, where distances are so vast that light itself takes millennia to cross them. This is the canvas of our cosmos. A place of breathtaking beauty, yes, but also one that conceals terrors beyond human imagination. We often gaze up at the stars with wonder, dreaming of exploration and discovery, but we rarely pause to consider what truly lies in that immense darkness. The universe is not just a collection of twinkling lights. It is home to phenomena so strange, so violent, and so utterly alien that they defy everything we think we know about reality. From black holes that devour light and time to cosmic voids where the laws of physics seem to break down, the universe harbors secrets that are as terrifying as they are fascinating. Today, we're setting aside the familiar comforts of our blue marble and venturing into the shadows. We'll be uncovering 25 of the most unsettling space horrors ever conceived or observed phenomena that challenge not only our understanding of the cosmos but our very place within it. This isn't just a list of scary facts, it's a journey into the unknown where the line between science and nightmare blurs. Some of these horrors are born from the extreme conditions of space itself, while others emerge from theories so profound they border on philosophy. What happens inside a black hole? Could the universe be conscious? Are we alone, or is something, or someone waiting in the dark? These questions tug at the edges of our curiosity and fear, inviting us to look deeper into the abyss, even as we wonder if the abyss is looking back. So prepare yourself. What you're about to discover will shift your perspective forever. This is not a tour for the faint of heart, but for those willing to confront the sublime and the terrifying in equal measure. As we move from one revelation to the next, remember, the universe is far stranger and far more mysterious than we often allow ourselves to believe. Let's begin. Our journey into the cosmic abyss begins not with a scream, but with a silent, inexorable pull. Imagine you are adrift in a vast cosmic river, carried along by a current you cannot see or feel, moving toward a destination hidden by a dense, impenetrable fog. This is not a metaphor, it is the reality for our entire galaxy and every galaxy in our local neighborhood. For decades, astronomers have known that the Milky Way is not stationary. It is racing through space at an astonishing 2 million kilometers per hour, but for the longest time, the reason for this immense velocity was a complete mystery. The force behind this motion is known as the Great Attractor, a gravitational anomaly of such incredible power that it is drawing hundreds of thousands of galaxies toward a single point in the universe, located in the direction of the Centaurus constellation. The sheer scale of this phenomenon is difficult to comprehend. To possess enough gravitational influence to tug on entire galaxies, the Great Attractor must be inconceivably massive. Early estimates suggested it had the pull of tens of thousands of Milky Ways combined. The problem, however, was that when scientists pointed their telescopes toward its predicted location, they found nothing. Or at least nothing they could clearly see. The core of our own galaxy blocks our view, creating a region astronomers call the zone of avoidance. This is a swath of the sky obscured by the gas, dust, and stars of the Milky Way's central bulge, effectively creating a blind spot that hides the very center of the mystery from our sight. For years, the Great Attractor remained one of cosmology's most frustrating puzzles, an unseen monster lurking in our own backyard, its true nature concealed behind a cosmic curtain. Breakthroughs in X-ray and radio astronomy eventually allowed us to peer through the obscuring veil, and what we found was both a resolution and a new, deeper mystery. The current leading theory suggests the Great Attractor is not a single, unimaginable object, but an immense concentration of mass known as the Laniakea supercluster. This is our galactic address on a grand scale, a vast filamentary structure of galaxies spanning 500 million light-years, of which our Milky Way is merely a suburban speck on a distant arm. Yet, even this colossal supercluster may not be the final answer. The pull we feel seems so strong that some scientists speculate the Great Attractor itself might be moving, drawn by something even larger and more massive behind it, a phenomenon they call the Shapley Attractor. This introduces the terrifying possibility of a cosmic matryoshka doll of gravitational influences, an endless chain of invisible forces pulling on forces that pull on us. We are caught in a celestial tide, flowing toward an attractor that is itself being attracted, forever unsure of the ultimate source. It is a humbling reminder that even as we map the cosmos, we are still subject to forces we cannot see, moving toward a destiny we cannot yet know. But if the idea of being pulled by unseen forces is unsettling, it pales in comparison to a threat that could erase the very fabric of reality itself, not with a pull but with a pop. This horror is born not from the vastness of gravity, but from the eerie quiet of quantum fields. To understand it, we must think of the universe not as a collection of stars and planets, but as a vast, bubbling sea of energy. Physicists believe that the fundamental forces and particles that make up our existence, the very laws of physics, are governed by the state of these underlying fields. And here lies the nightmare. What if the state our universe currently enjoys is not the truest, most stable state possible? What if we are all living in a cosmic lie, a precarious bubble of false stability they call a false vacuum? Imagine the universe is like a vast, tranquil mountain valley blanketed in a deep, peaceful fog. This fog represents our current reality, the laws of physics that allow for atoms, chemistry, and life. It feels permanent and absolute, but this valley, we come to learn, is actually perched on the edge of an impossibly high cliff. Below it lies a much deeper, truer valley, a state of lower energy that represents the true vacuum. Our universe, in this metaphor, is not in its lowest possible energy state. It's metastable, temporarily stable, but primed for a catastrophic change. All it would take is one tiny, random quantum event, a single metaphorical pebble dislodged, to trigger the collapse. The mechanism of this doom is as merciless as it is simple. Somewhere in the universe, a quantum fluctuation could spontaneously create a microscopic bubble of this true vacuum. The laws of physics inside this bubble would be completely different, utterly alien, and likely incompatible with any form of existence as we understand it. The true vacuum represents a lower energy state, and nature always seeks the lowest energy. The moment this bubble forms, the walls of this new reality would begin expanding in all directions at the speed of light. This isn't an explosion of matter, it is a wave of fundamental change, rewriting the laws of physics as it goes. There would be no warning, no distant rumble to alert us. The wave would be traveling at the ultimate speed limit of the cosmos, meaning we could not see it coming. 1 nanosecond, our universe exists with all its galaxies, stars, and lives. The next, the wavefront arrives, and everything, every particle, every force, every memory and moment is instantly and permanently erased, replaced by a new, unknown reality. It would be the ultimate and final extinction event, not just for life, but for the very concept of space-time. The cosmos would continue, but it would be a cosmos in which we, and everything we know, never could have existed. The most terrifying aspect of vacuum decay is its absolute inevitability if the theory is correct. It could happen 5 billion years from now, or it could have already begun in some distant galaxy, its wave of annihilation already on its way, silent, unstoppable, and light-speed fast. If the silent, inevitable wave of vacuum decay represents a universal end, our next horror is far more personal, a predator in the dark. We tend to picture black holes as stationary monsters, anchored at the hearts of galaxies or in binary star systems, their terrible appetites marked by glowing accretion disks. But this is a comforting illusion. The cosmos is home to a far more terrifying breed, the rogue black hole. These are the loners, the exiles, cast out from their galactic homes to drift forever in the immense, empty blackness between the stars. They are the ultimate ghost ships, invisible and silent, their presence betrayed only by the subtle, sinister warping of the very space they move through. How does a black hole, an object of such immense gravity, become a wanderer? The answer lies in the violent dynamics of galaxy formation and collision. When two galaxies merge, the supermassive black holes at their centers will eventually dance toward each other, drawn into a tightening orbital embrace. As they spiral in, they fling stars away like grains of sand and release colossal ripples in space-time known as gravitational waves. The final act of this cosmic merger is a catastrophic event. The two black holes plunge together, and if the merger is asymmetrical, if the gravitational waves are shot out more powerfully in one direction than the other, the newborn, larger black hole can receive a tremendous kick. This recoil can be so powerful that it ejects the black hole entirely from its galaxy, sentencing it to an eternal journey through the intergalactic void. This is where the true terror takes root. A rogue black hole, especially a stellar mass one, would be virtually undetectable until it was already upon us. Without a cloud of hot gas to feed on, it produces no bright accretion disk to give it away. It is a perfect assassin cloaked in its own lightless nature. It would not announce its approach with a blaze of light, but with a gradual, inexplicable distortion of the heavens. As it entered the outer reaches of a solar system, its gravitational influence would begin to tug on the delicate orbital ballet of planets. The first sign might be a single, distant planet's orbit becoming slightly more elliptical, then another. The subtle perturbations would ripple inward, a silent tremor in the fabric of our cosmic neighborhood. The potential outcomes range from the disastrous to the utterly apocalyptic. A distant, high-speed flyby, I might merely slingshot a few comets from the Oort cloud inward, triggering a minor asteroid shower or a new ice age on Earth. A closer pass could destabilize planetary orbits entirely, sending worlds like Mars or Venus careening into new, chaotic paths that could see them collide with Earth or be flung out of the solar system altogether. And in the worst-case scenario, a direct approach, the black hole would simply consume. It could pass straight through our solar system, its tidal forces tearing planets apart into streams of superheated rubble before swallowing them whole. The Sun itself could be pulled from its stable position, either devoured or sent spiraling away into the deep freeze of interstellar space, leaving the frozen, shattered remnants of our world behind. The most frightening thought is that this is not a theoretical possibility. Astronomers estimate there could be millions of these dark wanderers roaming our galaxy alone. One could be passing through our interstellar neighborhood right now, and we would have no way of knowing until its gravitational fingers had already begun to twist the paths of the worlds around us. Yet for all the silent, gravitational dread of a rogue black hole, there exists a threat from the cosmos that is its polar opposite, a scream of pure energy so violent and so brilliant it can outshine entire galaxies in the blink of an eye. We have navigated the quiet pull of the abyss and the silent pop of quantum decay. Now we must confront a horror that announces its arrival with the most powerful flash in the universe. These are gamma-ray bursts, the death cries of massive stars or the final, catastrophic mergers of stellar corpses. In a few seconds, a single burst can release more energy than our Sun will emit across its entire 10 billion-year lifespan. It is a cosmic event of almost unimaginable violence, and if one were to occur too close to our own pale blue dot, it would not merely be a spectacle in the sky, it would be an apocalypse. To understand the sheer power of a gamma-ray burst, we must first understand its origins. Astronomers classify them into two main types, each born from a different kind of stellar catastrophe. The longer bursts, lasting more than 2 seconds, are thought to be the final act of a very specific kind of star, a massive, rapidly spinning Wolf-Rayet star. When such a star exhausts its nuclear fuel, its core collapses instantly, forming a black hole. But the story doesn't end there. As matter plummets toward this newborn singularity, it doesn't all fall in directly. Some of it is channeled by the star's immense magnetic fields and spun up into two opposing, incredibly narrow jets of plasma and radiation, erupting from the star's poles at nearly the speed of light. These jets, focused and concentrated like cosmic blowtorches, are the gamma-ray burst itself. They blast through the outer layers of the dying star and scream across the universe, carrying with them the energy of a stellar suicide. The second type, short gamma-ray bursts, are briefer but no less intense. They are believed to be the product of a different kind of cosmic violence, the merger of two ultra-dense neutron stars or a neutron star and a black hole. As these incredibly massive objects spiral into each other, they too can launch focused jets of energy, creating a short, immensely powerful flash of gamma rays. In both cases, the key to the burst's destructive potential is that focus. The energy is not released in all directions like a bomb, but concentrated into two narrow beams. This means the burst is only visible and only lethal to any planetary system unfortunate enough to be looking directly down the barrel. And this is where the scenario transforms from a fascinating astronomical phenomenon into a genuine cosmic horror. If a gamma-ray burst were to occur within a few thousand light-years of Earth, and if one of its jets were pointed directly at us, the consequences would be swift and devastating. The first sign would be a flash of light in the sky so bright it would be visible even in the daytime, potentially brighter than 1,000 suns. But this would not be ordinary light. It would be an onslaught of high-energy gamma radiation and X-rays slamming into our atmosphere. This initial barrage would instantly rip apart the molecules in our upper atmosphere, specifically targeting the ozone layer that protects all life on Earth from the sun's harmful ultraviolet rays. In a matter of seconds, this protective shield could be obliterated, depleted by 50% or more. The immediate flash would be followed by a longer, lasting afterglow across other wavelengths, but the real, lingering damage would have already been done. With our planet's sunscreen scrubbed away, the surface would be bathed in lethal levels of ultraviolet radiation from our own sun. Land-based and shallow water ecosystems would collapse. Plant life would wither and die, breaking the foundation of the food chain. Animals, including humans, would suffer catastrophic rates of mutation, cancer, and blindness. The event would likely trigger a mass extinction event on par with the asteroid impact that wiped out the dinosaurs, but with a cruel, invisible hand. There would be no great fireball or impact winter. Instead, the world would slowly, painfully bake under a suddenly hostile sun, a silent casualty of a stellar explosion that occurred light years away. The chilling reality is that we know this has likely happened before. Some scientists point to the Ordovician mass extinction around 440 million years ago as a possible candidate, an event that wiped out a tremendous amount of marine life and fits the geological profile of a sudden ozone depletion. Our galaxy is a bustling stellar metropolis, and while the odds of a nearby burst are low on human timescales, they are not zero over the vast expanse of geological time. We orbit a relatively quiet star in a relatively quiet neighborhood, but the universe is a dangerous place, capable of unleashing destruction from across unimaginable distances with no warning and no malice, simply as a consequence of its own violent, indifferent physics. After confronting the silent, invisible threat of a rogue black hole and the blinding, apocalyptic fury of a gamma-ray burst, we are left with a different kind of terror, one born not from what is out there, but from what we cannot hear. We have scanned the heavens with our most powerful instruments, listening for a whisper, a signal, a sign that we are not the only conscious beings in this vast cosmic ocean. And yet, the universe answers only with a deafening, profound silence. This enigma is known as the Fermi Paradox, and it presents a horror that is deeply philosophical, deeply personal, and potentially far more frightening than any stellar catastrophe. The paradox is named for physicist Enrico Fermi, who, during a casual conversation about the high probability of extraterrestrial civilizations in the 1950s, simply asked, "But where is everybody?" His point was devastatingly simple. Our galaxy is ancient, roughly 13 billion years old, and contains hundreds of billions of stars. Many of these stars are older than our Sun and are orbited by planets in the habitable zone where conditions could be right for life to emerge. If even a tiny fraction of these planets developed intelligent life, and if even a smaller fraction of those civilizations developed the technology for interstellar travel or communication, the galaxy should be teeming with activity. It should be a bustling interstellar metropolis filled with the radio chatter of countless cultures, the wake of generation ships, and the unmistakable megastructures of advanced beings. The cosmic silence, therefore, is not just puzzling, it is deeply unsettling. It suggests that something is terribly wrong. This is where we encounter the most grim resolution to the paradox, the concept of the Great Filter. The Great Filter is a hypothesized barrier, a wall of improbability or catastrophe that prevents life from advancing to the stage of colonizing the galaxy. The terrifying question is not if the filter exists, but where it is located on the timeline of a civilization's development. Is it behind us or is it ahead of us? One possibility offers a glimmer of hope. Perhaps the filter is in our past. The leap from non-living chemistry to simple, self-replicating life might be so astronomically unlikely that it has only happened once in our galaxy, right here on Earth. Or perhaps the jump from single-celled life to complex, multicellular organisms is the true bottleneck. If this is the case, we are the lone miracle, the only ones to have made it this far. We are alone, and the silence is simply the sound of an empty galaxy. The far more terrifying alternative is that the Great Filter still lies in our future. This hypothesis suggests that the development of an intelligent, technological civilization inevitably leads to its own destruction. The silence we hear is not the silence of an empty nursery, it is the silence of a graveyard. Every civilization that reaches our level of technological maturity may hit a wall from which there is no return. This wall could take many forms. It could be the existential risk of nuclear self-annihilation, a war fought with weapons that erase a species from existence. It could be the unintended consequences of a runaway biotechnology, an engineered pathogen that escapes the lab and ends everything. It could be the rise of a hostile superintelligence that sees its creators as an obstacle to be removed. Or it could be that the very act of industrialization triggers an environmental collapse so severe that the planet can no longer support a technological society, forcing an irreversible decline. The silence of the Fermi Paradox, then, becomes a cosmic warning siren. It suggests that the reason we haven't heard from anyone is because no one makes it through the technological adolescence we are currently experiencing. The galaxy may be littered with the fossilized remains of civilizations that, like us, looked up at the stars with wonder only to be silenced by their own inventions. We are listening for neighbors, but we may only be listening for ghosts. Every new technological breakthrough, from artificial intelligence to genetic engineering, could be another step toward our own filter, another potential trigger for the same cosmic quiet that has swallowed everyone else. The universe isn't silent because it's empty, it's silent because it's lethal. Yet for all the grim finality of a great filter, the true nature of the cosmos might hold an even more fundamental and disquieting truth, one that renders our entire existence a mere afterthought in a universe dominated by forces we cannot see, touch, or comprehend. We have built our understanding of reality on the matter that surrounds us, the planets, the stars, our own bodies. But this is a cosmic illusion, a grand deception. The stuff we know and are made of the atoms forged in stellar furnaces accounts for less than 5% of the universe. The remaining 95% is composed of two utterly mysterious and invisible entities, dark matter and dark energy. They are the true masters of the cosmos, and their influence paints a future of profound isolation and emptiness. Let's begin with dark matter, the universe's unseen skeleton. We cannot detect it with any telescope because it does not emit, absorb, or reflect light. Its presence is known only through its gravitational pull. When astronomers observed galaxies spinning, they found a puzzle. The stars at the outer edges were moving far too quickly. According to the laws of gravity, these speeding stars should have been flung off into the void like mud spinning off a too fast tire. The only explanation was that each galaxy must be surrounded by an enormous, massive halo of something invisible, its gravity providing the extra pull needed to hold the fast-moving stars in place. This something is dark matter. It is the cosmic glue that binds galaxies together and the scaffolding upon which the entire visible universe is built. Without it, galaxies would never have formed in the first place. The ordinary matter was simply not enough to collapse into the structures we see today. But the effects of dark matter are even stranger than just providing extra gravity. Its presence warps the fabric of space-time so severely that it bends the path of light itself, a phenomenon known as gravitational lensing. We can see distant galaxies stretched and magnified into surreal arcs and rings around these invisible concentrations of mass, a ghostly fingerprint of the dark matter's distribution. We know it is there, we can map its influence, but after decades of search with the most sensitive detectors ever built, we have no idea what it actually is. It could be a sea of exotic, undiscovered particles that barely interact with normal matter, or it could be something even more bizarre, a substance that defies our current understanding of physics entirely. We are living in a universe dominated by a ghost, a silent partner whose nature remains one of the greatest unsolved mysteries in all of science. If dark matter is the hidden force holding the cosmos together, its counterpart, dark energy, is the hidden force determined to tear it all apart. In the late 1990s, two teams of astronomers made a discovery that shook the foundations of cosmology. They were measuring the distances to extremely far-off supernova, expecting to find that the expansion of the universe was slowing down over time due to the gravitational pull of all the matter within it. Instead, they found the opposite. The expansion is not slowing, it is accelerating. The universe is blowing itself apart at an ever-increasing rate. Something is counteracting gravity on the largest scales, a repulsive force woven into the vacuum of space itself. This something is dark energy. The leading theory suggests dark energy is a property of empty space, an intrinsic energy of the vacuum that causes new space to constantly generate, pushing galaxies away from each other. As the universe expands, more space is created, which in turn creates more repulsive force, leading to a runaway acceleration. The implications for the far future are nothing short of horrifying. We are headed for a fate known as the heat death or the big freeze. As the expansion accelerates, distant galaxies will first redden as their light is stretched into undetectable wavelengths, and then they will vanish entirely beyond an unreachable cosmic horizon. Eventually, the universe will be a vast, ever-cooling emptiness. Our local group of galaxies may remain gravitationally bound, but everything beyond will disappear from view, leaving any future civilization with the utterly false impression that they are alone in a static island universe. The cosmos will become an eternal, expanding void, cold, dark, and empty, with the scattered remnants of stars and galaxies fading into ultimate equilibrium. The great cosmic story will end not with a bang, but with the silent, inexorable whisper of dark energy, ensuring that everything that ever was is forever forgotten in an infinite, lonely dark. But if dark energy provides the engine for this bleak future, the physics that governs it leads to an even more profound and chilling conclusion. This is the concept of the heat death, the ultimate victory of entropy, and the final, irreversible state of the cosmos. To grasp the terrifying inevitability of this fate, we must first understand entropy. In the simplest terms, entropy is a measure of disorder, a statistical law of the universe that states systems will always trend from a state of order to a state of disorder. It's the reason a hot cup of coffee left on a table will eventually cool to room temperature, but a room temperature cup will never spontaneously heat up. The energy in the universe behaves in the same way. It is constantly spreading out, diffusing, and becoming less useful. For billions of years, stars have acted as incredible engines against this trend. They are temporary pockets of intense, concentrated order, drawing in diffuse hydrogen gas and through nuclear fusion, creating heavier elements and releasing enormous amounts of light and heat. Life itself is a magnificent local rebellion against entropy, building complex, ordered structures from the energy provided by our star. But this is a battle that cannot be won, only delayed. Every star that shines is ultimately converting usable fuel into waste heat and light that radiates out into the cold void of space. They are not creating new energy, they are merely spending the universe's finite supply, one brilliant transaction at a time. The heat death is the point where this spending reaches its conclusion. It is the moment the universe effectively runs out of things to do. All the usable energy, the differences in temperature and density that drive every process from galaxy formation to human thought, will have been evenly distributed across an immeasurably vast and ever-expanding volume. The temperature everywhere will approach absolute zero, the point where all atomic motion ceases. There will be no more stars to form, as the raw hydrogen gas will have been entirely consumed or drifted too far apart to ever coalesce again. No more planets will orbit these dead suns. The black holes themselves, the last bastions of immense gravitational order, will have slowly evaporated over trillions upon trillions of years due to Hawking radiation, their mass converted into a final, feeble whisper of energy that too will dissipate into the void. The universe will not end in fire or ice, but in a state of perfect, eternal equilibrium. It will be a cosmos without events, without change, and without time in any meaningful sense. Time requires a before and an after, a sequence of cause and effect. But in a universe where every point is identical to every other point in temperature and energy, where no processes can occur, the very concept of time loses all meaning. It will be the deepest, most absolute silence imaginable, a silence not of sound but of action. This is the true horror of the heat death. It is not an explosive end, but an infinite, unchanging fade to black. It is the assurance that every achievement, every memory, and every trace of every civilization that ever existed will not just be forgotten, but will become physically impossible to ever occur again. The cosmos will be a static, lifeless graveyard forever. Yet even the grand, inevitable fade of the heat death is not the only silent threat lurking in the cosmos. There exists another horror, one that defies the very life cycle we assign to the stars. We are taught that stars live and die in a predictable sequence, but what if death is not the end? What if a star, long cold and dead, could be violently resurrected, its corpse reanimated into a brief, brilliant, and utterly destructive second life? This is not the stuff of fantasy. It is a real astronomical phenomenon, and it creates some of the most powerful explosions in the universe. We are talking about zombie stars, specifically white dwarfs that return from the grave in a cataclysm known as a Type Ia supernova. To understand this stellar resurrection, we must first understand the corpse itself. A white dwarf is the final ember of a star like our Sun. After such a star exhausts its nuclear fuel, it gently sheds its outer layers, leaving behind an incredibly dense, Earth-sized core of mostly carbon and oxygen. This is a white dwarf. It no longer generates energy through fusion. It simply glows with residual heat, destined to cool over trillions of years into a cold, dark black dwarf. It is the epitome of stellar death, a fading cinder, but this peaceful end is only guaranteed if the white dwarf is left alone. The horror begins when it is not. A white dwarf possesses a terrifying property. It has a strict, non-negotiable maximum mass known as the Chandrasekhar limit. If a white dwarf's mass is pushed beyond this critical threshold, about 1.4 times the mass of our Sun, the immense gravitational pressure reignites nuclear fusion in its core with apocalyptic violence. Unlike the steady fusion of a living star, this is a runaway thermonuclear explosion. The entire white dwarf detonates in a matter of seconds, completely unbinding itself in a supernova so bright it can outshine an entire galaxy. There is no remnant left behind. The star is entirely vaporized, its atoms forged into heavy elements like iron and gold and scattered across the cosmos. The key question is, how does a dead star suddenly gain the extra mass needed to cross this line and trigger its own destruction? There are two primary, monstrous pathways to this stellar resurrection. The first is a slow, gruesome process of cosmic cannibalism. If a white dwarf is in a binary system with a living star, its intense gravity can begin to strip material away from its companion. This stolen gas, mostly hydrogen, spirals down onto the surface of the white dwarf, accumulating in a dense, hot layer. For a time, this layer may fuse hydrogen in a series of smaller, surface nova explosions, but the real danger builds beneath. The white dwarf itself is steadily gaining mass with every stolen mouthful. If this slow accretion continues for long enough, pushing the white dwarf over the Chandrasekhar limit, the core conditions suddenly become hellish enough to fuse carbon. The entire star then undergoes an instantaneous thermonuclear chain reaction, resulting in a Type Ia supernova. The second pathway is far more violent and direct, a collision. In dense star clusters, the gravitational dance can become chaotic, and two white dwarfs can be flung into a catastrophic head-on collision. When these two ultra-dense corpses smash together, their combined mass instantly and dramatically exceeds the Chandrasekhar limit, triggering the same titanic thermonuclear detonation. This is a quicker, more brutal form of resurrection, a sudden impact that results in instantaneous annihilation. The sheer power of these events is difficult to overstate. A single Type Ia supernova can release as much energy in a few weeks as our Sun will over its entire 10 billion-year lifetime. But the true danger of a nearby zombie star eruption is not the blinding light, it is the invisible shrapnel. The explosion floods the surrounding space with a lethal wave of high-energy radiation, gamma rays, X-rays, and cosmic rays. If such an event were to occur within a few dozen light-years of Earth, this radiation barrage would strike our planet with devastating force. It would shred our protective ozone layer, just as a gamma ray burst would, exposing the surface to the Sun's deadly ultraviolet radiation and effectively giving the entire planet a lethal sunburn. The resulting ecosystem collapse would almost certainly cause a mass extinction event. The most frightening aspect is the unpredictability. A white dwarf is a silent, dark, and nearly invisible object. We may not even know one is lurking relatively nearby until it suddenly begins its feast on a companion star, building toward its own destruction and potentially ours. Our solar system orbits in a fairly quiet suburb of the galaxy, but the Milky Way is home to billions of these stellar corpses. A close binary system containing a white dwarf could be edging toward its doom unseen, its resurrection poised to unleash a silent wave of death across light years of space. It is a reminder that in the cosmos, even death is not always a permanent state, and the dead can sometimes rise with a vengeance that threatens the living. But the slow, cold fade of the heat death is not the only destiny that dark energy might have in store for the cosmos. There exists a far more violent and immediate alternative, an end so brutal it would tear the very fabric of reality apart at the seams. This is the nightmare scenario known as the Big Rip. To understand it, we must look more closely at the mysterious force driving our universe's accelerating expansion. The leading model for dark energy is called a cosmological constant, a steady, unchanging force inherent to the vacuum of space. But what if dark energy is not constant? What if it is something far more potent and terrifying, a force that grows stronger over time? This hypothetical form of dark energy is known as phantom energy, and its existence would not just lead to an expanding universe, but to one that literally explodes from the inside out. The horror of the Big Rip lies in its timeline and its utter disregard for the structures we think of as fundamental. In this scenario, the repulsive force of phantom energy doesn't just push galaxies apart, it increases in strength as the universe expands. Eventually, its push would become stronger than the forces that hold the universe together. This isn't a competition it would lose. The end would come in a cascading series of destructions, a cosmic unraveling that would happen not over countless eons, but within a remarkably short and terrifyingly finite window. Imagine a countdown to oblivion where the very bonds of existence are systematically severed. The first casualties would be the largest gravitational structures. With the expansion accelerating at an ever-increasing rate, the phantom energy's repulsive force would eventually exceed the gravitational glue holding galaxy clusters together. These vast cities of stars would be flung apart, their constituent galaxies becoming isolated islands drifting in a rapidly widening void. But the acceleration wouldn't stop there. Next, the force would grow strong enough to overcome the gravity binding individual galaxies themselves. The Milky Way, along with every other galaxy, would be torn asunder. Stars would be ripped from their orbital paths and sent hurling into the expanding darkness, each one becoming a lonely beacon in an ever more empty universe. The true terror, however, begins when the expansion strength targets smaller and smaller structures. In the final moments, the phantom energy's repulsive force would become greater than the electromagnetic forces that hold matter together. First, planetary systems would be shredded. The sun's gravitational hold on Earth would be broken, and our planet would be flung away from its dying star. Then the Earth itself would come apart. The force would exceed the gravity that holds our planet together, and it would simply burst, fragmenting into a cloud of rocks and dust. But the destruction would continue, drilling down to the most fundamental level. The force would eventually overcome the chemical bonds holding those rocks together, reducing them to individual atoms. And in the last infinitesimal fraction of a second before the end, the repulsive force would become stronger than the nuclear forces that bind atomic nuclei together. Protons and neutrons would be torn apart, and even atoms themselves would be vaporized into a soup of fundamental particles. The universe would end not with a fading ember, but with every single piece of matter, every atom in every star, planet, and person, being simultaneously and violently ripped into its most basic components. Space-time itself, the very stage upon which the cosmic drama plays out, would be shredded beyond recognition, potentially ceasing to exist in any coherent form. It is the most total and violent apocalypse physics can conceive, a final, definitive end to everything. But if the explosive resurrection of a white dwarf represents a sudden, all-consuming fire, our next horror is a far more precise and relentless threat. A celestial sniper rifle that never runs out of ammunition. We have encountered stars that die in supernova and leave behind black holes or quiet white dwarfs, but there is a third, far more active corpse. When a massive star explodes, its core can be crushed with such incredible force that protons and electrons are fused together into neutrons, creating a city-sized ball of almost pure nuclear material so dense that a single sugar cube-sized fragment would weigh as much as a mountain. This is a neutron star, and while many of these ultra-dense remnants are relatively quiet, some of them are bestowed with two terrifying properties: a mind-boggling rate of spin and a magnetic field of almost incomprehensible power. This specific type of neutron star is known as a pulsar, and it is one of the most precise and deadly objects in the universe. The birth of a pulsar is a violent and chaotic event, but its aftermath is a masterpiece of terrifying order. As the star's core collapses, the principle of the conservation of angular momentum takes over. The same principle that causes an ice skater to spin faster when they pull their arms in. A star that may have rotated once every few weeks is suddenly compressed into an object only 12 miles across, causing its spin to accelerate dramatically. Some pulsars rotate hundreds of times every single second, their surfaces moving at a significant fraction of the speed of light. At the same time, the star's original magnetic field is compressed and intensified until it becomes 1 trillion times stronger than Earth. This monstrous magnetic field acts like a cosmic particle accelerator, capturing charged particles and funneling them toward the star's magnetic poles. As these particles rain down, they generate intense beams of radiation across the entire spectrum, from radio waves to visible light to lethal X-rays and gamma rays erupting from the magnetic poles. Because the magnetic axis is often misaligned with the star's rotational axis, these beams of death do not shine steadily. Instead, they sweep through space like the beams of the most powerful lighthouse ever conceived. With every rotation, these focused cones of radiation slash across the darkness, and from our distant vantage point, we observe this as a rapid, precise pulse, a blink-on, blink-off signal of incredible regularity. This is the pulsar's namesake heartbeat, a ticking clock born from stellar catastrophe. The true horror of a pulsar is not its pulse, but what that pulse represents, a focused, sweeping scythe of energy. For any planetary system unlucky enough to be within the sweeping path of this beam, the consequences would be apocalyptic. Imagine a world orbiting a star that happens to lie in the pulsar's line of sight. For most of its orbit, the planet might be perfectly habitable, enjoying the light and heat of its sun. But then, at regular, predictable intervals, the pulsar's beam sweeps across it. In that moment, the planet is bathed in a flash of radiation so intense it would be like holding the entire output of a star, focused into a narrow blade directly against its atmosphere. This is not a gentle wash of light, it is a sterilizing blast. Each pass of the beam would deliver a staggering dose of high-energy X-rays and gamma rays, systematically stripping away the planet's ozone layer and irradiating the surface. The effect would be a slow, grisly cookery. Complex organic molecules would be broken apart. Any life that had managed to gain a foothold, from simple microbes to more complex organisms, would be repeatedly scoured from the face of the world with the regularity of a metronome. The planet would become a cosmic shooting gallery, hit with a lethal pulse of radiation every few seconds, minutes, or hours, ensuring that life could never again establish itself. It would be a world trapped in a cycle of partial recovery and utter annihilation, forever cursed by the relentless ticking of a dead star. What makes this scenario particularly chilling is the potential for these death beams to operate over immense distances. While a pulsar's beam is focused, it can remain coherent and deadly for many light years. Our solar system has likely already been swept by such beams from distant pulsars, and while they were too far away to cause harm, it is a stark reminder that we live in a galaxy populated by these silent, rotating sentinels of death. They are the universe's ultimate keepers of bad time, their ticking not marking the hours but counting down the possibilities for life in their eternal, sweeping path. While we often look to the deep cosmos for existential threats, one of the most immediate and tangible horrors is being constructed by our own hands, not in the distant void but in the space just above our heads. We have surrounded our planet with a shell of our own ingenuity, thousands of satellites that enable our global communication, navigation, weather forecasting, and national security. But this shining ring of technology has a dark twin, a growing cloud of high-speed junk that threatens to turn our greatest achievement into an inescapable prison. This is the Kessler syndrome, a nightmare scenario where a single collision in orbit triggers an unstoppable chain reaction, encircling Earth with a swirling storm of shrapnel that could render spaceflight impossible for generations. The danger lies not in the size of the debris, but in its velocity. In low Earth orbit, where the International Space Station and most satellites reside, objects are moving at staggering speeds of roughly 28,000 kilometers per hour. At that velocity, even a fleck of paint or a tiny screw carries the kinetic energy of a cannonball. A collision with a fragment the size of a marble would be catastrophic, capable of completely destroying a multi-billion-dollar satellite or punching a fatal hole through a manned spacecraft. Each such impact doesn't just remove one piece of debris. It creates thousands of new, smaller fragments, each one a new bullet in the cosmic shooting gallery. This is the core of the Kessler syndrome proposed by NASA scientist Donald Kessler in 1978. A cascading collision chain where each crash exponentially increases the amount of debris, which in turn makes further collisions more likely, until certain orbital pathways become so saturated with shrapnel that they are effectively unusable. We are already seeing the early warning signs of this cascade. In 2009, a defunct Russian Cosmos satellite collided with an active American Iridium communications satellite, instantly creating over 2,000 new pieces of large, trackable debris and countless smaller fragments that are still threatening other assets today. In 2007, China deliberately tested an anti-satellite missile by destroying one of its own weather satellites, an act that single-handedly increased the amount of trackable debris in low Earth orbit by 25%. Each of these events scattered clouds of metal across orbital highways, forcing the International Space Station and other satellites to perform regular debris avoidance maneuvers to dodge the ever-growing field of junk. The tipping point, the moment the Kessler syndrome becomes a true horror, is when the density of debris reaches a critical threshold and the chain reaction becomes self-sustaining. Even if we were to never launch another rocket, the collisions would continue on their own, each one feeding the next. The result would be a dense, abrasive shield of shrapnel encircling our planet. Reaching orbit through this cloud would become a suicidal gamble, akin to flying a plane through a hurricane of supersonic bullets. The launch windows for interplanetary missions would slam shut, trapping humanity on Earth just as we were reaching for the stars. Our satellites, the fragile nervous system of our global civilization, would be systematically shredded. GPS would fail, plunging global transportation and logistics into chaos. Weather forecasting would revert to the technology of a century ago, unable to see major storms forming over the oceans. Global communications and banking networks would falter. We would be plunged into a new technological dark age, looking up at a sky we can no longer access, surrounded by the silent, twinkling remnants of our own ambition. The greatest horror of the Kessler syndrome is that it is a problem of our own making, a slow-motion disaster we can see coming, and one that we are still struggling to find the will and the technology to prevent. But for all the silent, existential threats we've explored, the cosmos also contains a form of destruction that is both majestic and brutally physical. We have spoken of silent decays and invisible forces, but the universe is also a stage for colossal, violent acts of consumption on a scale that dwarfs any terrestrial predator. This horror is known as galactic cannibalism, the process by which large galaxies gravitationally tear apart and absorb their smaller neighbors. It is a fundamental force of cosmic evolution, and it is a fate that our own Milky Way is both a perpetrator of and a future victim. The mechanism is as simple as it is terrifying: gravity. A large galaxy, with its immense halo of dark matter and billions of stars, exerts a powerful gravitational pull on any smaller galaxy that ventures too close. The smaller galaxy does not simply crash into the larger one like a car into a wall. Instead, it is subjected to a slow, agonizing process of tidal disruption. Imagine the difference in gravity between the side of the small galaxy facing its giant captor and the side facing away. This difference creates immense tidal forces, the same kind of forces that the Moon uses to pull on Earth's oceans, but amplified to a cosmic and destructive degree. These forces begin to stretch the victim galaxy, pulling it apart like cosmic taffy. Long streamers of stars, gas, and dust are drawn out, forming brilliant, looping arcs that wrap around the larger galaxy, the gravitational scars of the meal. Many of these stars are flung entirely out of their galaxy, condemned to wander the intergalactic void as lonely, orphaned suns. Others are pulled into new, chaotic orbits within the larger galaxy, their once stable paths thrown into disarray. The event is not a quick death, but a drawn-out feast that can take hundreds of millions of years to complete. We see the evidence of this carnage all around us. The large Andromeda Galaxy, our nearest major neighbor, is ringed by these stellar streams, the remnants of dozens of smaller galaxies it has consumed over its lifetime. Our own Milky Way is currently in the process of digesting several smaller galaxies, including the Sagittarius dwarf spheroidal galaxy, which has been stretched into a long filament of stars that wraps around our galactic home. This brings us to the most personally relevant act of galactic cannibalism, the future collision between our Milky Way and the Andromeda Galaxy. For a long time, this was thought to be a remote possibility, but Hubble Space Telescope measurements have confirmed it is an inevitability. In approximately 4.5 billion years, these two spiral giants will meet. The initial interaction will be a breathtaking, slow-motion car crash lasting millions of years. The galaxies will first swing past each other, their gravitational pull warping each other's structures, stretching their spiral arms into long, distorted tails of stars. Then they will fall back together, merging over another 2 billion years into a single, giant elliptical galaxy that astronomers have nicknamed Milkdromeda. For any beings living within either galaxy at that time, the direct threat to life would be surprisingly low. The distances between stars are so vast that actual stellar collisions are exceedingly unlikely. The real danger comes from the gravitational chaos. The serene, predictable orbital dance of stars within the galactic disk will be thrown into turmoil. Stars like our Sun could be flung from the galactic suburbs into the chaotic inner core, or even ejected into the intergalactic darkness altogether. This would violently disrupt the delicate ecosystems of any life-bearing planets, not through impact but by altering their cosmic environment. A star sent plunging through the dense, radiation-filled galactic center would expose its planets to deadly cosmic rays and nearby supernova. A star ejected into the cold, empty void would see its planets frozen solid, their sun becoming a lonely beacon in an unimaginable darkness. This process reveals a humbling truth about our place in the cosmos. We think of galaxies as permanent, stable islands in the void, but they are not. They are dynamic, evolving creatures in a constant state of consumption and growth, built upon the cannibalized remains of their smaller neighbors. Our peaceful spiral Milky Way is a product of this violent history, and its serene beauty is a temporary state in a cycle of creation and destruction that will eventually see its form erased forever, consumed into the featureless blaze of an elliptical galaxy. It is a reminder that even the largest structures in the universe are subject to the relentless, hungry pull of gravity. Yet even as we confront the terrifying finality of cosmic collisions and cascading debris, a far more intimate and mind-bending horror awaits. One that challenges not just our place in the universe, but the very nature of our own existence. This horror emerges not from the vastness of space, but from the bizarre and counterintuitive world of quantum mechanics. It's a theory that suggests consciousness itself might play a role in shaping reality, leading to a deeply unsettling possibility known as the quantum immortality paradox. This idea proposes that from a subjective point of view, you might never actually experience your own death, not because you are special, but because the universe might continuously branch to ensure you always find yourself in a reality where you survive. To grasp this unsettling concept, we first need to understand the many worlds interpretation of quantum mechanics. In the quantum realm, particles don't exist in a single defined state. Instead, they exist in a haze of probabilities called a superposition. A particle is simultaneously here, there, and everywhere until it is observed. The classic thought experiment is Schrödinger's cat, where a cat in a box is both alive and dead until someone looks inside. The many worlds interpretation offers a radical solution to this paradox. It suggests that at the moment of observation, the universe doesn't choose a single outcome. Instead, it splits into multiple, equally real branches. In one universe, the observer finds a live cat. In another, they find a dead one. Both events happen, but in separate, non-communicating timelines within an ever-branching multiverse. Now, apply this logic to your own life and mortality. Imagine you are placed in a diabolical experiment. A gun is pointed at your head, rigged to a quantum trigger. Perhaps it's controlled by the decay of a single radioactive atom. There is a 50% chance the gun will fire and a 50% chance it will not. From an outside perspective, this is a simple game of chance. Half the time you die, the other half you live. But from your subjective first-person perspective, what happens? If the gun fires, your consciousness in that branch ceases. But if it does not fire, your consciousness continues. The many worlds interpretation suggests that both outcomes are real. In one branch, you are dead. But in the other, you are alive and wondering why the gun didn't go off. Now repeat the experiment again and again. Each time, the universe splits. In half the branches, you die, but in the other half, you survive. From your perspective, you will only ever experience the branches where you continue to exist. No matter how many times you pull the trigger, you will always be the version of yourself that hears a click. You become subjectively unkillable, not through invulnerability, but through a continual branching of reality that always places your stream of consciousness in a timeline where you, against all odds, survive. This is the quantum immortality paradox, the suggestion that you might never subjectively witness your own death, because the moment of death is a state you cannot experience. Your consciousness will always follow the path where it persists. The existential dread this induces is profound and multifaceted. It leads to a lonely form of solipsism, where you might begin to wonder if you are the only truly real consciousness, with everyone else merely being part of a branching reality that exists to ensure your continued observation. It also raises terrifying questions about the nature of aging. Would an immortal consciousness simply continue branching into realities where it survives catastrophic illnesses, accidents, and disasters, only to eventually find itself the last living human in a universe slowly succumbing to entropy, unable to die yet utterly alone? This isn't a theory that offers comfort. It suggests a potential eternity of isolation where death is not an end, but an endless avoiding of ends. It transforms the universe from a cold, physical place into a potentially subjective prison, where the one thing you can never confirm is your own cessation. You can never prove you are immortal, but you can also never prove you are not. The horror lies in the absolute uncertainty and the profound isolation of a consciousness that might, by its very nature, be forced to continue forever. But if the quantum realm offers a terrifyingly personal form of immortality, our next horror returns us to the grand scale of the cosmos, to an emptiness so vast and profound it challenges our very understanding of the universe's structure. We have spoken of dense clusters, violent explosions, and the gravitational pull of immense attractors, but we must now journey into the opposite extreme, a region of nothingness. This is the Boötes void, one of the largest known cavities in the observable universe, a spherical desert of space so empty it has earned the nickname the Great Nothing. Stretching an almost inconceivable 330 million light-years across, this void is not merely a less populated neighborhood. It is a cosmic ghost town of epic proportions, a staggering absence that forces us to question what could possibly have carved such a hole in the fabric of the cosmos. To grasp the sheer scale of this emptiness, we must first understand what a normal region of space looks like. On average, the universe is speckled with galaxies. In a typical cube of space with sides 100 million light-years long, astronomers would expect to find several thousand galaxies. Within the Boötes void, that number plummets to a mere 60 or so. That's not 60,000, it's 60 total. This means the void is overwhelmingly, almost perfectly empty. If our Milky Way were located at the center of the Boötes void, the night sky would be nearly black. Without powerful telescopes, humanity might never have known other galaxies even existed until the 20th century. Forever trapped in an island universe with no visible neighbors, our cosmology built on a foundation of profound isolation. The existence of such a void is a profound puzzle for cosmologists. The prevailing model of the universe's evolution, the Big Bang theory combined with inflation, predicts that matter should be distributed in a web-like structure, long filaments of galaxy clusters surrounding vast, empty bubbles. But the Boötes void is so exceptionally large that it strains this model. How could a region this empty form? One leading theory suggests that smaller voids, which are common, can merge over time like soap bubbles coalescing into one giant bubble. Another, more unsettling idea is that the void might be the result of a collision with another universe in the multiverse, a scar left by a physics we cannot yet comprehend. Or perhaps it is simply a statistical fluke, a 1 in a trillion underdensity that by pure chance happened to occur. But its very existence reminds us that our models are incomplete, and the universe might contain structures whose origins are completely unknown to us. This leads to a deeper, more philosophical horror, the fear of true isolation. For any hypothetical civilization that might have arisen within such a void, the cosmic perspective would be one of utter loneliness. Their telescopes would peer into a deep blackness in almost every direction, their universe effectively ending at the boundaries of their own local group of galaxies. They would have no evidence of the larger cosmic web, no grand tapestry of galaxies to inspire them to look outward. They might logically conclude that they are utterly alone in existence, the sole flicker of light and life in an infinite, eternal dark. Their science might never conceive of the Big Bang or the expanding universe, for they would see no red shift of fleeing galaxies, no evidence of a dynamic cosmos. They would be prisoners in a gilded cage, their entire reality confined to an island in a sea of nothing, forever unaware of the bustling universe that lies beyond their dark horizon. The Boötes void stands as a monument to cosmic loneliness, a chilling reminder that the universe is not only full of wonders and horrors, but also of immense, silent, and inexplicable absences. Yet for all the colossal, impersonal forces shaping our galaxy's fate, the most immediate threat to our technological civilization may come from the one object we trust most, our own sun. We think of it as a constant, a reliable source of light and warmth that has nurtured life for billions of years. But our sun is not a placid, unchanging ball of fire. It is a dynamic and occasionally violent star, capable of fits of rage that could, in an instant, hurl us back into a pre-industrial age. While we fear the cataclysmic explosions of distant stars, we often overlook the danger lurking in our own backyard, the potential for a solar superflare, an eruption of magnetic energy hundreds of times more powerful than any event in recorded human history. To understand a superflare, we must first understand the more common solar flares and coronal mass ejections that our sun produces on a regular 11-year activity cycle. These events are born from the sun's tangled magnetic fields. Like enormous rubber bands being twisted and stretched, these fields can suddenly snap, reconnecting with a catastrophic release of energy. A solar flare is that intense flash of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. It is a burst of light that reaches Earth at the speed of light, taking just over 8 minutes to arrive. Often accompanying a flare is a coronal mass ejection, or CME, a slower-moving but far more massive cloud of magnetized plasma billowing out from the Sun's atmosphere. When a CME is aimed at Earth, it can trigger a geomagnetic storm, a disturbance in our planet's magnetic field that has very real consequences. We have already witnessed a taste of what a powerful solar storm can do. In 1859, the Carrington event, named after the astronomer who observed the accompanying solar flare, sent a CME slamming into Earth's magnetosphere. The resulting geomagnetic storm was so powerful that telegraph systems, the advanced technology of the day, sparked and caught fire, and operators could send messages even after disconnecting their batteries, powered solely by the electrical currents induced in the wires by the storm. Auroras were seen as far south as the Caribbean. While spectacular, the event caused limited damage because the world's technological infrastructure was in its infancy. A storm of that magnitude today would be catastrophic. Our modern world is woven together by a vastly more complex and fragile web of electronics and power grids. A direct hit from a Carrington-level event would induce powerful electrical currents in long-distance power lines, overwhelming transformers and causing cascading blackouts that could span continents. Satellites would be fried by the radiation, disabling GPS, communications, and weather monitoring. Banking systems, water treatment plants, and supply chains would grind to a halt. The recovery could take years, if not decades. This is the known danger. The true horror, however, lies in the possibility that our Sun is capable of something far worse than a Carrington event. By studying other stars similar to our own, astronomers have discovered evidence of superflares, stellar eruptions that release energy not just hundreds, but hundreds of thousands of times greater than the largest solar flare we have ever observed. These events are detected when a star's brightness suddenly increases by a significant percentage for a short period, a sign of a colossal release of magnetic energy. For a long time, it was assumed that such superflares only occurred on young, rapidly spinning stars or stars in close binary systems where tidal forces could stir up magnetic activity. Our middle-aged solitary sun seemed like an unlikely candidate for such extreme behavior. However, recent data has shattered that comforting assumption. Surveys from space telescopes like Kepler have revealed that Sun-like stars, stars of similar mass, age, and composition, do indeed experience these monstrous superflares, albeit very rarely. The statistics suggest that a star like our Sun might produce a superflare capable of devastating a technological civilization once every few thousand years. The mechanism is thought to be the same as a normal flare, just on a titanic scale, the sudden reconnection of magnetic field lines. But in a superflare, the magnetic energy reservoir is unimaginably larger, perhaps generated by a hyperactive sunspot group far larger than any we have ever seen. The consequences of such an event directed at Earth are almost too grim to contemplate. The initial flash of extreme ultraviolet and X-ray radiation would violently expand our upper atmosphere, increasing drag on low-orbiting satellites and causing them to plummet back to Earth. The pulse of radiation would then slam into our planet, creating a massive electromagnetic pulse, or EMP, that would induce devastating currents in any conductor on the sunlit side of the globe. It would be an instantaneous planetary-scale electrical surge. Every unprotected microchip, every power grid, every transformer, and every electronic device would be instantly fried. The world would be thrust into a global blackout in the blink of an eye, with no way to quickly replace the destroyed infrastructure. We are not talking about a temporary inconvenience. We are talking about the permanent end of the digital age. The long-term effects could be even more severe. such a tremendous influx of energy could potentially chemically alter the atmosphere, damaging the ozone layer on a global scale and exposing all life to heightened levels of mutagenic ultraviolet radiation from the sun. The very star that gave us life could, in a single fit of rage, strip away the technological shell we have built around ourselves and threaten the biological world beneath. The evidence from other stars tells us this is not science fiction. It is a real, albeit low probability, threat written in the light of our stellar neighbors, a silent warning that our sun is not always the gentle guardian we believe it to be. But for all the cataclysmic violence of solar storms and galactic collisions, the cosmos holds a more subtle, creeping form of terror, one that doesn't blaze with the fury of a star, but instead wanders in perpetual frozen silence. We have so far focused on threats that announce their presence with brilliant flashes or immense gravitational pulls. Yet some of the most common and haunting objects in the galaxy are those that give off no light at all. These are the rogue planets, dark, frozen worlds that have been violently ejected from their parent star systems and now drift alone through the interstellar void. Astronomers now believe these orphaned worlds may vastly outnumber stars in our galaxy, perhaps by a ratio of 20-1, making them the true silent majority of the Milky Way, a hidden population of ghost worlds forever untethered from the warmth of a sun. The birth of a rogue planet is a story of cosmic violence and chaos. In the early, turbulent days of a star system's formation, the gravitational dance between nascent protoplanets is a brutal free-for-all. As these young worlds jockey for position, close gravitational encounters can act like a slingshot, flinging a smaller, unfortunate planet out of the system entirely. It is ejected at tremendous speed, cast adrift into the blackness between the stars, its solar orbit exchanged for an eternal journey around the galactic core. This process is surprisingly common. Simulations suggest that for every star system that successfully forms, it may create and eject multiple such planets into the darkness. These worlds are not merely drifting, they are fleeing, forever escaping the scene of their violent birth. The conditions on such a world are the stuff of true science fiction horror. Without a star to provide light and warmth, the surface temperature plummets to just a few degrees above absolute zero. The atmosphere, if it had one, would freeze solid, collapsing into a blanket of snow that settles on a landscape of permanent, airless night. Any surface features, mountains, valleys, plains, would be frozen into an eternal, static tableau, illuminated only by the faint, unmoving glow of the distant galactic disk. There would be no sunrise, no sunset, no seasons, just an endless, deep freeze darkness where the very concept of time loses its meaning. The only changes would come from the unimaginably slow process of geological decay and the occasional, rare impact from another piece of interstellar debris. Yet, within this frozen hellscape, a tantalizing possibility for life persists, one that transforms these rogue planets from mere frozen tombs into potential arks. Many of these ejected worlds are likely to be gas giants or ice giants, but a significant number could be terrestrial planets, similar in size to Earth or Mars. If such a world possessed a subsurface ocean, kept liquid by geothermal heat from a radioactive core or tidal flexing from a large moon that was ejected with it, that ocean could persist for billions of years beneath a shell of ice many kilometers thick. This creates the possibility of an isolated subsurface biosphere, completely cut off from the rest of the universe. Life could flourish around hydrothermal vents on the ocean floor, in an ecosystem entirely independent of solar energy, powered instead by the planet's internal heat. These would be the most isolated living things in existence on a world with no star, adrift in the galactic night, utterly unaware that any universe exists beyond their icy ceiling. The true existential threat of a rogue planet, however, lies in its potential to invade our own celestial neighborhood. Given their sheer numbers and dark, invisible nature, the statistical probability that one could pass through our solar system is not zero. The approach would be utterly silent and undetectable until it was very close, as it would reflect virtually no light. The first sign of its arrival would be a subtle gravitational disturbance in the outer solar system, a slight wobble in the orbits of distant Kuiper belt objects. As it drew closer, its gravity would begin to tug on the gas giants, then the inner planets, acting like a cosmic bull in a celestial china shop. The consequences of a close pass would be catastrophic. It could destabilize the orbits of every planet it passed, potentially sending Earth into a new, deadly elliptical orbit that would freeze and bake the planet alternately. It could fling Mars or Venus into a collision course with us. It could even eject Earth from the solar system entirely, sending our world on its own eternal journey into the frozen dark as a new rogue planet, our sun shrinking to just another star in the blackness until even that light vanished. The galaxy may be filled with these dark wanderers, and one could be on a collision course with our solar system right now, and we would have no way of knowing until its gravitational fingers were already twisting the paths of the worlds around us. But if rogue planets represent a dark, frozen threat wandering the galaxy, our next horror strikes at the very heart of our understanding of reality, born from the most destructive objects in the universe. We've seen how black holes can devour stars and planets, but they might also be consuming something far more fundamental, the very rules that govern the cosmos. This is the black hole information paradox, a puzzle so profound that it has divided physicists for decades and suggests that at its core, reality might not play by the rules we think it does. To understand this, we must first grasp a sacred principle of quantum mechanics. Information cannot be destroyed. In the quantum world, information is not just data. It is the complete set of properties that describe every particle in the universe, its mass, its spin, its position. This information is never lost. It can only be transformed, scrambled, or rearranged. If you could somehow reverse all the motions and interactions of every particle in a burned book's ashes and the surrounding smoke and heat, you could, in theory, reconstruct the book perfectly. The information is always preserved. Now, introduce a black hole into this pristine picture. According to Einstein's general theory of relativity, a black hole is defined by just three simple properties: its mass, its electric charge, and its spin. This is often called the no-hair theorem, meaning black holes have no other distinguishing features, no complicated hair. Here lies the paradox. Imagine you throw an incredibly detailed, information-rich object into a black hole, say, a computer hard drive containing every piece of knowledge humanity has ever gathered. According to general relativity, that object crosses the event horizon and is irretrievably lost. The black hole's mass, charge, and spin might increase slightly, but the specific, intricate information about the arrangement of particles that made up that hard drive is seemingly erased from the universe. It is gone, and the three simple numbers that now describe the black hole provide no hint of what was lost. This violates the fundamental quantum law that information must be preserved. The plot thickened with Stephen Hawking's groundbreaking work. He showed that black holes are not completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles now known as Hawking radiation. This radiation, according to Hawking's original calculations, is purely thermal. It is random noise like the heat radiating from a stove, and it contains no information whatsoever about what fell into the black hole. So, when the black hole finally evaporates completely and vanishes, what happens to the information from that hard drive? If the only thing that comes out is random thermal radiation, then the information has been truly and permanently destroyed. This pitted two pillars of modern physics against each other: quantum mechanics, which insists information is eternal, versus general relativity, which, when combined with Hawking's calculation, seemed to show it could be erased. This paradox suggests something is terribly wrong with our understanding of physics. If information can be lost, then the universe is fundamentally unpredictable. The past does not dictate the future in a reliable way, and the very foundation of cause and effect crumbles. Physicists have proposed several potential resolutions, each more mind-bending than the last. One idea is that the information is not lost at all, but is somehow encoded on the event horizon itself, the point of no return. In this holographic principle, the three-dimensional information of everything that falls in is smeared across the two-dimensional surface of the black hole like a cosmic hologram, and it is slowly leaked back out in the Hawking radiation over eons. The universe, in this view, might itself be a hologram, a projection from a two-dimensional surface at its boundary. Another, more radical suggestion is that there is no inside. The event horizon might be a blazing firewall of incredible energy that instantly incinerates anything that touches it, preserving the information in the resulting radiation, but making the classic idea of falling into a black hole a deadly illusion. The most unsettling resolution, however, is that the information really is lost, and we must simply accept that the fundamental laws of physics are not what we thought. The black hole information paradox is not just an academic debate. It is a crisis that forces us to question whether reality is built on a foundation of predictability or chaos, and whether the most extreme objects in the universe are hiding the final, terrifying secret of existence itself. But the silent, wandering threat of a rogue planet is born from gravitational chaos, a casting out into the cold. There is another cataclysm, however, that represents a final, violent embrace, a collision of the universe's most extreme and dense objects. We have spoken of the immense power released when a white dwarf crosses a mass limit, but that is a thermonuclear firecracker compared to the titanic detonation that occurs when two neutron stars meet. This is the horror of a neutron-star merger, an event of such staggering violence that it warps the fabric of space-time itself and forges the very elements we hold precious, all while threatening any nearby world with a silent, radioactive death. To set the stage for this cosmic catastrophe, we must first appreciate the players involved. A neutron star is the collapsed core of a massive star that went supernova but wasn't quite massive enough to form a black hole. It is a ball of pure nuclear matter, a city-sized object that packs more mass than our sun. A single teaspoon of its material would weigh billions of tons. These objects are so incredibly dense that their surfaces are likely smooth, perfect spheres harder than any diamond, and their gravity is so intense that if you were to drop a marshmallow onto one from a height of 1 meter, it would impact with the energy of a nuclear bomb. Now imagine two of these ultra-dense, unforgiving objects locked in a gravitational dance of death. They begin their lives as a binary system, two massive stars that lived, died, and left their neutron star cores behind. Emitting gravitational waves, ripples in space-time caused by their orbital motion, they slowly lose energy, spiraling inexorably closer over millions of years. As they draw nearer, the pace quickens, their orbital dance becomes a frenzied whirl, and in the final moments they orbit each other thousands of times per second, moving at a significant fraction of the speed of light. The gravitational waves they emit during this final plunge become a shriek in the fabric of the cosmos, a rising tone that crescendos in what astronomers call a chirp, a signal that our most sensitive instruments on Earth, like LIGO and Virgo, can now detect across vast intergalactic distances. The moment of impact is beyond comprehension. When these two neutron stars finally collide, they do not simply crack together like billiard balls. The event is a maelstrom of physics run amok. The collision releases a blinding flash of gamma rays. A short gamma ray burst as the intense magnetic fields and pressures launched jets of material and energy screaming out from the poles of the merger. Simultaneously, the outer layers of the neutron stars are ripped away and flung into space at incredible velocities. Within this expanding cloud of superheated neutron-rich matter, known as a kilonova, the universe undertakes its most spectacular act of alchemy. In the heart of a star, fusion can only create elements up to iron. Creating heavier, neutron-rich elements like gold, platinum, and uranium requires a rapid capture of neutrons, a process known as the R process. A neutron-star merger provides the perfect, hellish environment for this. The cloud of debris is so dense with neutrons that atomic nuclei are bombarded, growing massive in a fraction of a second before radioactively decaying into stable, heavy elements. It is in these fleeting, violent moments that the gold in a wedding ring, the platinum in a catalytic converter, and the uranium in a power plant are forged. A single merger can create hundreds of Earth masses worth of gold and other heavy elements, scattering them across the galaxy to be incorporated into future generations of stars and planets. Our own solar system is likely enriched with the radioactive ashes of such a cataclysm that occurred long before the Sun was born. Yet, for all its creative power, a neutron-star merger is also a weapon of mass destruction on a galactic scale. The initial gamma-ray burst is a focused beam of lethal radiation, but even for planets not directly in its path, the aftermath holds a more insidious and widespread threat. The kilonova cloud expands, filled not only with newly minted gold, but also with a vast amount of radioactive isotopes, unstable elements like uranium and plutonium that decay, emitting high-energy radiation for thousands of years. If such an event were to occur within a few thousand light-years of Earth, our planet would be showered with this radioactive fallout. The initial gamma-ray burst would be a fleeting, apocalyptic flash for any world in its direct line of fire, but the real, lingering horror would come from the slow and silent rain of radioactive particles that follows. This fallout would permeate the interstellar medium and eventually drift into our solar system, continuously bombarding Earth for centuries. It would act like a slow-acting poison, increasing the background radiation levels across the entire planet. This would lead to elevated rates of cancer and genetic mutations across all species, potentially triggering a long, drawn-out extinction event that would slowly strangle the biosphere. There would be no spectacular impact winter or immediate fireball. Instead, life would gradually sicken under an invisible, radioactive drizzle, a grim reminder of a beautiful, creative, and utterly deadly event that occurred light years away. The very elements that make our technology and adornments possible were born from a cataclysm that, if it happened too close, would ensure that no civilization would ever be around to use them. After exploring the radioactive fallout from cosmic collisions and the paradoxes of quantum information, we are forced to confront a horror that is not born from the universe, but one that questions the very nature of the universe itself. This idea suggests that the cosmos, with all its galaxies, black holes, and physical laws, may not be the fundamental base layer of reality. Instead, it could be an elaborate construct, a sophisticated simulation running on some form of technology so advanced it is indistinguishable from reality itself. This is the simulation hypothesis, a concept that transforms the existential dread of cosmic insignificance into a deeply personal crisis of authenticity, where the greatest terror is the potential for the simulation to be paused, altered, or terminated by unseen, godlike creators. The argument for this possibility is deceptively simple and, to many, disturbingly persuasive. It begins with the assumption that any sufficiently advanced civilization would eventually develop the capability to create immersive, high-fidelity simulations of reality, perhaps as a form of historical research, entertainment, or scientific experimentation. Given the vast age of the universe and the potential for countless civilizations to have arisen long before our own, the number of such simulated realities could be astronomically high, far outnumbering the one base reality. If that is the case, the statistical probability that we are living in that one original reality, rather than one of the countless simulations, becomes vanishingly small. We are far more likely to be simulated beings than organic ones. This logic, first popularized by philosopher Nick Bostrom, is a modern, technological twist on Descartes' demon, replacing the malevolent spirit with a hyper-advanced computer program. The immediate horror this induces is not one of physical destruction, but of existential vertigo. If this is a simulation, then our entire history, every triumph and tragedy, every personal memory, every emotion of love and loss, could be nothing more than lines of code or curated data points in a grand experiment. The laws of physics we strive to understand would be merely the programmed parameters of the simulation, potentially changeable at the whim of the operators. This reduces our struggles, our art, our very consciousness to a kind of advanced puppet show, robbing our existence of any intrinsic meaning or purpose. The universe becomes a gilded cage of predetermined events, and the concept of free will transforms into a terrifying question. Are our choices truly our own, or are they simply the inevitable output of a complex, predetermined algorithm? This leads to the most active form of horror within the hypothesis, the potential for intervention. If we are in a simulation, we are subject to the actions of the simulators. They could, at any moment, decide to alter the parameters of our reality for their own inscrutable purposes. They might introduce glitches, change physical constants, or even pause the simulation entirely. The fear of being shut down is the ultimate existential threat, not just death, but the complete and instantaneous erasure of our entire universe from whatever server it runs on. There would be no warning, no appeal, and no aftermath. One moment everything exists, the next there is nothing. It is a threat that makes the heat death of the universe seem almost comforting in its natural, predictable inevitability. Furthermore, the creators might not be benevolent scientists, but something far more sinister. They could be bored children in a post-human civilization, treating our suffering as a form of entertainment. They could be malicious hackers attempting to corrupt the simulation from the inside, or the simulation's purpose could be utterly alien and incomprehensible to us, making our lives and struggles as meaningful as the flickering pixels in a forgotten screensaver. The complete lack of agency and the inability to ever know the true nature or intentions of our creators is a profound and unique form of cosmic helplessness. Yet, some scientists and philosophers argue that the hypothesis might actually be testable. If our universe is a simulation, it might contain detectable artifacts or limitations, much like a video game has a render distance or a resolution limit. Some have proposed that we might find evidence in the very high-energy cosmic rays we observe. If space-time is discretized on a fantastically small scale, a fundamental pixel size for the simulation, we might see a cutoff in the energy of these particles, as they cannot be rendered beyond the program's maximum capacity. Others look for potential glitches or errors in the consistency of physical laws. The search for such evidence is a bizarre and fascinating frontier of science, where the tools of physics are being used to potentially prove we are living in a digital creation. Whether proven or disproven, the simulation hypothesis forces a profound philosophical shift. It compels us to look at the bedrock of reality not as a given, but as a question, and to wonder if the true masters of the cosmos are not dark matter or black holes, but programmers whose motives we can never hope to understand. Yet after wrestling with the possibility that our reality might be a digital fiction, we can look to the sky for what seems like the most concrete evidence of our origins, the cosmic microwave background. This faint, cold glow is the oldest light in the universe, the cooled remnant of the Big Bang's primordial fireball, and it paints the entire sky with a nearly perfect uniformity. For decades, it has been the cornerstone of our cosmological models, a snapshot of the infant cosmos that confirms its explosive birth and subsequent expansion. But what if this ancient baby picture, this most trusted piece of evidence, contains subtle, terrifying flaws? What if, etched into this fossilized light, are clues that our universe is not the pristine, isolated bubble we believe it to be, but has instead been scarred by a collision with another cosmos entirely. This horror begins with a simple, chilling fact: the cosmic microwave background is too perfect. The early universe, according to the standard model, was a searingly hot, dense soup of particles and energy. As it expanded and cooled, light was finally able to travel freely, creating the glow we detect today. The incredible uniformity of this background radiation's temperature, it's the same in every direction to within a tiny fraction of a degree, was a major puzzle. How could regions of the universe on opposite sides of the sky, which could never have been in contact with each other due to the finite speed of light, have reached the exact same temperature? The solution was the theory of cosmic inflation, a period of faster-than-light expansion in the universe's first fraction of a second that smoothed everything out to this incredible degree. This theory predicted that while the background would be mostly uniform, it would still contain tiny, random fluctuations, the quantum seeds that would later grow into galaxies and galaxy clusters. Our powerful satellites like Planck have mapped these fluctuations in exquisite detail, and they mostly match the predictions beautifully. But it is in the deviations from perfection, the strange anomalies, where the true cosmic dread resides. The most famous and unsettling of these anomalies is known as the cold spot. This is a region in the constellation Eridanus that is significantly colder than the surrounding sky, a vast circular patch of space that is cooler by about 70 microkelvins. While that sounds insignificant on the incredibly smooth canvas of the cosmic microwave background, it stands out like a massive, icy bruise. At first, astronomers thought it might be a mere artifact, a trick of the data. But repeated observations have confirmed it is real. The simplest explanation would be that it is not a feature of the background radiation itself, but something in the foreground, a gigantic void, an immense region of space with far fewer galaxies than average, which the light had to pass through. As light travels through such an underdense region, it loses a tiny amount of energy, an effect known as the integrated Sachs-Wolf effect, which could potentially create a cold spot. But when astronomers went looking for this supposed Eridanus supervoid, they found nothing large enough or empty enough to account for the profound cold. The void they did find was far too small to explain the anomaly. The cold spot refused to be explained away. This is where cosmology steps from the reassuringly known into the realm of the terrifyingly speculative. If no known structure within our universe can cause the cold spot, then perhaps its cause lies outside our universe. The most compelling and frankly alarming theory is that the cold spot is the imprint of a collision between our universe and another bubble universe in the vast multiverse. The theory of eternal inflation suggests that our universe is just one expanding bubble in a foaming, infinite multiverse, where new universes are constantly budding off from the inflationary background, each with its own possibly different laws of physics. In this chaotic, infinite foam, these bubble universes could sometimes collide. If our young, still-forming universe were to brush against another such bubble, the energy of that collision would be transferred at the boundary. The result inside our universe would be a vast, circular region where the energy density was slightly different, affecting the cosmic microwave background in that exact location and creating a spot that is colder than its surroundings. The cold spot in this interpretation is nothing less than a cosmic scar, a permanent bruise left by a collision with another reality. The implications of this are staggering. It suggests that our universe is not alone and is not perfectly insulated. It exists within a wider, arguably hostile meta-reality where such collisions are possible. What if the other universe had fundamentally different physical laws? The collision could have been far more than a gentle bump. It could have been a cataclysmic event that violently rewrote the rules of physics in that region of space, creating a zone of absolute existential alienation within our own cosmos. It raises the terrifying possibility that such collisions could happen again. If our universe is still moving through the multiversal foam, what is to stop another, potentially larger bubble from colliding with us? A future collision could be far more than a mere imprint on background radiation. It could be an existential threat. The boundary where the two universes meet could be a wall of sheer nothingness or a region where physics becomes chaotic and unpredictable. A wave of unreality that propagates through the cosmos at the speed of light, erasing stars, planets, and physical laws as it goes. The cosmic microwave background, that serene and reassuring map of our origins, suddenly becomes a potential warning sign, telling us that the quiet of our universe is an illusion, and that we are adrift in a multiverse we cannot see, unable to predict when the next potentially devastating collision might occur. Far beyond the familiar orbits of Neptune and Pluto, beyond the scattered disk of the Kuiper belt, lies the true final frontier of our solar system, a vast spherical shell of frozen relics known as the Oort cloud. This is not a compact ring of debris, but an immense and diffuse reservoir of trillions of icy planetesimals, leftovers from the solar system's formation that were flung into the deepest reaches by the gravitational interactions of the young giant planets. The scale of this region is almost impossible to fathom. It begins roughly 2,000 astronomical units from the Sun and stretches outward for perhaps 100,000 astronomical units, nearly halfway to the next star. This places the inner edge of the Oort cloud nearly 50 times farther from the Sun than Neptune, while its outer boundary dissolves into the interstellar void. These icy bodies, some as large as mountains, drift in a perpetual, slow-motion dance around our star, so distant that the Sun is merely the brightest star in their sky, its light a faint, cold pinprick incapable of providing any warmth. The true terror of the Oort cloud is not its existence, but its profound instability and our utter helplessness against the forces that can stir it. These frozen worlds are so far away that the Sun's gravitational grip on them is tenuous at best. They exist in a precarious balance, their orbits easily perturbed by the slightest external influence. The most common disruptor is the gentle, constant tidal pull of the galaxy itself. As our solar system oscillates up and down through the plane of the Milky Way, the collective gravity of billions of distant stars exerts a subtle but persistent tug on these icy bodies. This galactic tide can slowly alter their orbits over millions of years, occasionally shaking one loose and sending it on a long, falling trajectory inward toward the heart of our system, where it becomes a long-period comet, a spectacular but potentially deadly visitor. But the galactic tide is a slow and predictable force. The genuine peril emerges from a far more random and violent source, a close stellar passage. Our solar system is not stationary. It moves through the galaxy, and other stars are moving on their own paths around the galactic center. Statistically, another star is expected to pass within 1 light year of our Sun roughly every 100,000 years. While that may seem like a safe distance, for the delicate gravitational ecology of the Oort cloud, it is an apocalyptic event. When a star, even a small red dwarf, ventures this close, its gravity acts like a colossal plunger shoved into a pond, creating a massive gravitational disturbance that ripples through the entire cloud. It doesn't just nudge a single comet, it can dislodge thousands, even millions of them, sending a swarm of icy missiles showering inward on orbits that will bring them through the inner solar system tens of thousands of years later. This scenario transforms the Oort cloud from a distant curiosity into a loaded gun perpetually aimed at our planet, with passing stars acting as invisible fingers on the trigger. We have likely already experienced this phenomenon. Many paleontologists and astronomers point to evidence of periodic mass extinction events in Earth's geological record, and some of these, particularly the extinction that wiped out the dinosaurs 66 million years ago, are attributed to asteroid impacts. However, other, less severe extinction pulses show a curious periodicity, and one compelling theory suggests they could be the result of these cometary showers triggered by close stellar passes. The impact of a comet, often larger and moving much faster than a typical asteroid, would be even more devastating, releasing unimaginable amounts of energy and potentially triggering global firestorms and a long, chilling impact winter. The most frightening aspect of this peril is its unpredictability and the immense lag time between cause and effect. A star could pass through our outer Oort cloud tomorrow, and we would have no way of knowing the cometary storm it had just unleashed. The comets themselves would take thousands of years to complete their journey sunward, giving no immediate warning. By the time the first new long-period comet is spotted by our telescopes, the vanguard of the swarm might already be upon us. We are living on a world that exists downstream from a celestial minefield, vulnerable to gravitational nudges from stars we may not even have identified yet. A reminder that our safety is an illusion maintained by the vast, empty distances of space distances that are not empty at all, but filled with silent, frozen sentinels waiting for a push. But if the silent gravitational tides of the Oort cloud represent a slow, external threat, the next horror is woven into the very fabric of spacetime itself, a personal and psychological torture born from one of Einstein's most brilliant and unsettling revelations. We think of time as a constant, a universal river flowing at the same rate for everyone, everywhere. This is our everyday experience, but it is a comforting illusion. According to Einstein's theory of relativity, time is not absolute, it is malleable, a fluid dimension that can be stretched and warped by two powerful forces, velocity and gravity. This phenomenon, known as time dilation, transforms the dream of interstellar travel into a potential nightmare of irreversible isolation and loss. To grasp how this works, imagine two identical clocks, both perfectly synchronized. One remains here on Earth, while the other is placed aboard a spacecraft capable of traveling at an appreciable fraction of the speed of light. According to special relativity, as the ship's velocity increases, time literally slows down for everyone and everything on board relative to the outside universe. This isn't a mechanical error or a perceptual trick. It is a fundamental property of the cosmos. The faster you move through space, the slower you move through time. From the perspective of the astronauts on the high-speed ship, their clock would seem to tick normally. Their hearts beat at a regular pace, their conversations flow as always. But if they could look back at the clock on Earth, it would appear to be racing forward at a frantic pace. Conversely, mission control on Earth would see the ship's clock frozen, barely ticking at all. Now apply this to a real journey. A crew embarks on a round-trip voyage to a star system 20 light-years away. Their ship is a marvel of engineering, allowing them to cruise at 90% the speed of light. For the crew, the journey might feel like it takes just a few decades due to the time dilation effect. They age those decades, but back on Earth over a century has passed. When they return triumphant, they step out onto a world that is utterly unfamiliar. Their children are older than they are, if they are even still alive. Their spouses, friends, and parents are long gone, buried by the relentless march of time that they themselves escaped. Their nation may no longer exist, their culture a relic of the past. They are living ghosts returned to a home that is not theirs anymore, their personal timeline severed from the rest of humanity. The triumph of discovery is instantly crushed by the overwhelming grief of losing everyone and everything they ever knew. This temporal dislocation is not limited to high-speed travel. It is also a terrifying product of intense gravity, as described by general relativity. The closer you are to a massive object like a black hole, the stronger the gravitational field and the more time slows down. Imagine a dedicated team of scientists on a mission to study a black hole up close. They pilot their ship into a stable orbit just beyond the event horizon, a region where gravity is so intense that time is dragged to a near standstill. For the crew, perhaps only a few hours pass as they collect their priceless data. But for the universe outside this gravitational well, thousands of years sweep by. They could complete their mission and return to find Earth unrecognizable. Their species evolved into something new or even extinct. Their entire civilization might be dust, their heroic effort forgotten by history before they even finished it. They would be the ultimate strangers, not just in space but in time. This is the unique and profound horror of time dilation. It is not a physical threat to the body, but an existential threat to the soul and our fundamental need for connection. It makes the cosmos not just a place of physical danger, but a labyrinth of temporal traps. A journey to the stars, the greatest adventure imaginable, carries with it the heaviest of prices, the guarantee that you can never truly return home. You can only ever return to a place that used to be home, a museum of a life you can never get back. It is a one-way ticket not just through space but through time, condemning the traveler to a future they were never meant to see, forever alone. After contemplating the chilling isolation of being untethered in time, we now turn our gaze to the largest scales imaginable, where the universe reveals an architecture so vast and intricate it seems almost designed. We have mapped the locations of billions of galaxies, and when we step back to look at this grand cosmic cartography, a pattern emerges from the apparent chaos. The universe is not a random sprinkling of stars and galaxies. It is structured, organized into a colossal web of unimaginable scale. This is the cosmic web, and within its filaments and nodes, astronomers are discovering subtle, colossal skeletons, ghostly frameworks that hint at a deep and perhaps unsettling order to existence. One of the most stunning examples of this is a recent discovery nicknamed the Gaia skeleton, a structure that forces us to confront the eerie possibility that the universe is built upon a blueprint we are only beginning to perceive. For decades, the prevailing cosmological model has predicted that the universe should resemble a web. The gravitational pull of dark matter, which makes up the majority of the universe's mass, is thought to have acted as an invisible scaffolding after the Big Bang. Ordinary matter, the gas that forms stars and galaxies, was then drawn into the densest regions of this dark matter framework. Over billions of years, this process constructed the universe we see today. Long, thin filaments of galaxy clusters intersecting at dense nodes surrounding vast, empty voids. We have inferred the existence of this web through complex computer simulations, but actually seeing it has been a monumental challenge because it requires mapping the precise three-dimensional positions of countless galaxies across immense volumes of space. This is where the Gaia spacecraft, a revolutionary mission by the European Space Agency, has changed the game. Gaia's primary goal is to create an extraordinarily precise three-dimensional map of our own Milky Way galaxy by measuring the positions and motions of over 1 billion stars. But its incredible data set has also allowed astronomers to peer beyond our galactic borders. By combining Gaia's measurements with other surveys, scientists can now chart the distribution of galaxies in our cosmic neighborhood with unprecedented detail. It is within this new, high-resolution map of local universe structure that researchers spotted something astonishing. A previously unseen, tendril-like arrangement of galaxies, a vast and coherent filament that curves through space. They called this structure the Gaia skeleton, a name that perfectly captures its role as a hidden bony framework upon which the flesh of galaxies is hung. The sheer scale of this skeleton is humbling. It is not merely a small string of galaxies, it is a major component of the cosmic web, a backbone of our local universe that helps define the boundaries of a nearby void. Its discovery was not just about finding another filament, it was about seeing the cosmic web in sharper focus than ever before, confirming that these immense structures are not just theoretical but are real, physical features of the cosmos. This skeleton and others like it are the highways and continents of the universe, shaping the flow of matter and the destiny of galaxies on scales that defy human comprehension. This leads us to the profound and slightly unnerving implication. The existence of such a precise, large-scale architecture suggests an underlying order that seems almost too perfect. The cosmic web, with its filaments and nodes, looks eerily similar to other complex networks we see in nature, from the neural pathways of a human brain to the intricate structure of a fungus's mycelium network. This similarity is so striking that it has sparked a bold and controversial field of study known as cosmopsychism, or the idea of a conscious universe. Could the universe itself be a form of consciousness? Is the cosmic web a kind of cosmic brain, with galaxies acting like neurons firing across the void? This is, of course, a highly speculative metaphor, not a scientific theory, but it resonates because it speaks to a deep human desire to find patterns and meaning in the cosmos. The Gaia skeleton forces us to ask whether the universe is not just governed by blind physical laws, but is in some way organized, perhaps even in a way that mirrors the structures of life itself. The true architect of this grand design, however, is almost certainly the mysterious, invisible hand of dark matter. We cannot see the Gaia skeleton's true form because the galaxies we observe are merely tracers, the visible lights decorating the underlying massive structure built from dark matter. The filament itself is predominantly made of this unknown substance, a gravitational foundation that dictated where galaxies could form. This means we are not truly seeing the skeleton, we are only seeing the glowing moss that grows upon it. The real structure remains hidden in plain sight, a ghostly architecture woven into the fabric of space-time, whose true nature and composition are completely unknown to us. We can map its gravitational influence, we can see its effects, but we cannot touch it or directly observe it. The universe, it seems, has a hidden framework, a dark anatomy that we are only beginning to trace out with our instruments. This realization is both a triumph of science and a source of deep cosmic awe, tinged with a subtle horror. It means that the universe is not only larger and more violent than we can imagine, but it is also more structured and organized in ways that we are fundamentally blind to. We live our lives in the visible universe, aware of only a tiny fraction of the actual mass and energy that shapes our reality. The Gaia skeleton is a reminder that we are living inside a colossal, intricate construct whose full blueprint is written in a language of dark matter and dark energy that we have not yet learned to read. We can see the shadows it casts, but the object itself remains elusive, a constant, haunting presence that suggests the cosmos is far more complex, far more ordered, and far stranger than the simple expanse of stars we see with our naked eyes. But even the intricate, awe-inspiring structure of the cosmic web is built upon a foundation of physical constants we take for granted: the mass of a proton, the charge of an electron, the strength of the forces that bind atoms together. These are the immutable rules of our universe, the settings that allow for the existence of galaxies, planets, and life itself. Yet, what if these very rules were not so immutable? What if our attempts to understand the deepest workings of reality could, in theory, trigger a chain reaction that would rewrite the rules entirely, erasing our universe in the process? This is the realm of the most speculative and existential of cosmic horrors, where scientific curiosity itself could become the ultimate weapon. These are not natural disasters, but potential catastrophes born from experimental hubris, often chillingly referred to as anti-blockbuster events, scenarios where the blockbuster experiment doesn't just succeed, but destroys everything. The most famous of these nightmare scenarios involves a hypothetical particle known as a strangelet. To understand this, we must venture into the bizarre world of quark matter. Most of the normal matter we know is made of atoms with nuclei containing protons and neutrons. These, in turn, are made of quarks. Protons and neutrons contain up and down quarks, which are the lightest and most stable varieties. However, theory suggests there could be a far more stable form of matter, known as strange matter, made of a soup of up, down, and strange quarks. Strange matter is thought to be incredibly dense and perfectly stable, a true ground state of matter. Under immense pressure and density, like that inside a neutron star, ordinary matter might spontaneously transform into this strange matter. The terrifying proposition is that a tiny piece of this substance, a strangelet, could be created in a high-energy particle collider like the Large Hadron Collider. If such a strangelet were created and if it were stable, a terrifying possibility arises. It could act as a catalyst. Upon contacting a nucleus of normal matter, it could convert that nucleus into strange matter. This conversion would release energy, making the growing strangelet even more stable and increasing its ability to convert more matter. In the worst-case scenario, this would initiate an unstoppable chain reaction. The entire Earth could be converted into an inert, hot lump of strange matter in a matter of seconds before anyone even realized what was happening. This apocalyptic idea was taken seriously enough that scientists at CERN conducted extensive safety reviews, concluding that the conditions in particle colliders are far less extreme than those naturally occurring in cosmic ray collisions throughout the universe's history. If strangelets could destroy the planet, the constant barrage of high-energy cosmic rays would have already done so billions of years ago. Yet, the theoretical possibility, however remote, taps into a deep-seated fear of scientific overreach, a modern-day equivalent of opening Pandora's box. An even more fundamental and devastating anti-blockbuster event revolves around the stability of the vacuum itself. We discussed the horror of vacuum decay earlier as a natural quantum event, but what if we could accidentally induce it? Some theories suggest that the vacuum we exist in is metastable, but that a far lower energy, true vacuum state exists. The energy barrier separating our false vacuum from this true one is immense, but not necessarily infinite. The concern, though entirely speculative, is that a high-energy particle collision could, by some freak chance, create a set of conditions that act as a key, unlocking that lower energy state. It would be like striking a match in a room filled with an unknown, invisible gas. The moment this microscopic bubble of true vacuum formed, the laws of physics inside it would be utterly alien. Crucially, this new state would have a lower energy, and nature always seeks the lowest energy state. The walls of this new reality would then begin expanding in all directions at the speed of light. This wouldn't be an explosion of matter, it would be a wave of fundamental change, rewriting the very laws of physics as it propagated outward. Atoms, forces, space-time itself, everything that makes our universe what it is, would be erased and replaced by something new and almost certainly incompatible with life or any structure we know. The wave would be unstoppable and undetectable until it arrived, as it moves at the ultimate speed limit. One moment the universe exists, the next it is gone, replaced by something unknowable. The probability of such an event is considered vanishingly small by virtually every physicist who has studied it. The energies we can achieve in our puny particle colliders are minuscule compared to the energies involved in natural cosmic events. If our experiments could create a universe-destroying bubble, then the far more energetic collisions happening constantly in the universe between cosmic rays inside neutron stars or in the hearts of active galaxies would have already triggered this cataclysm eons ago. The universe's continued existence is the best evidence that our experiments are safe. Yet the philosophical horror remains potent. It represents the ultimate fear of the unknown, the anxiety that our thirst for knowledge could inadvertently lead to our own total and absolute erasure. It is the pinnacle of existential risk, not from an external threat like an asteroid or a gamma-ray burst, but from within, from our own tools and our own intellect. These anti-blockbuster scenarios, while firmly in the realm of science fiction given our current understanding, serve as a powerful metaphor. They are cautionary tales about responsibility, the limits of knowledge, and the humbling reality that we are tampering with forces whose ultimate consequences we cannot fully predict, playing with matches in a cosmic tinderbox whose true nature we are only beginning to glimpse. Yet after exploring the universe's hidden architecture and the terrifying potential of our own experiments, we are drawn to the ultimate question, the final horror that overshadows all others. What is the destiny of the cosmos itself? We have journeyed through threats to our planet, our star, and even our reality. But now we must confront the inevitable end of everything, the ultimate fate of the universe. This is not a story with a single ending. Cosmology offers us several potential final chapters, each more grand and humbling than the last, stretching across timelines so vast they dwarf human comprehension. The prevailing theory, the one that currently aligns best with our observations of dark energy, points toward a slow, cold, and silent demise known as the heat death. Imagine all the energy in the universe, the brilliant fury of stars and the gentle warmth of planets, gradually spreading out until it is evenly distributed across an ever-expanding volume of space. The temperature everywhere would approach absolute zero, the point where all atomic motion ceases. Stars would burn out one by one, their ashes scattered and too diffused to ever form new ones. Black holes, the last bastions of order, would themselves slowly evaporate over trillions of years through Hawking radiation. The universe would become a thin, cold soup of particles, utterly dark and stagnant. There would be no more events, no changes, no processes of any kind. Time itself would become meaningless, as there would be no before or after, no cause and effect to measure its passage. This is the ultimate victory of entropy, a state of perfect equilibrium where the cosmos simply runs out of things to do. But the heat death is not the only possible finale. Before the discovery of dark energy's accelerating push, many scientists favored a more dramatic, cyclical ending, the Big Crunch. In this scenario, the collective gravitational pull of all the matter in the universe would eventually overcome the momentum of the Big Bang's expansion. The cosmos would stop expanding, pause for a moment, and then begin rushing back inward. Galaxies would merge in a violent frenzy, and the temperature of the universe would skyrocket. All of existence would be compressed into an infinitely hot, infinitely dense singularity, a mirror image of the Big Bang itself. For some, this was a comforting idea, suggesting a potential cycle of death and rebirth, a phoenix universe that could explode into a new Big Bang from the ashes of the old one. This concept, sometimes called the Big Bounce, proposes an eternal cycle of expansion and contraction, with each new universe potentially born with different physical constants. Yet our current observations of accelerating expansion have made the Big Crunch seem far less likely, leaving the cold, fading whisper of the heat death as the most probable outcome. A third and far more violent possibility is the Big Rip. This scenario depends on dark energy not being constant but growing stronger over time, a hypothetical form called phantom energy. In this terrifying end, the repulsive force of dark energy would eventually overcome every force that holds the universe together. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration increased, its ferocity would grow stronger than the gravity holding our solar system together, flinging planets away from their dying sun. Then it would exceed the forces holding planets and stars together, tearing them apart into clouds of dust. In the final moments, the force would become stronger than the very nuclear forces that bind atoms together. Every proton, every neutron, every fundamental particle would be violently shredded in a simultaneous, catastrophic end to all structure. The universe would cease to exist not with a slow fade, but with a sudden, definitive scream of space-time itself being ripped apart at the seams. Reflecting on these cosmic demises, the true horror is not the manner of the end, but its sheer inevitability and scale. We are living in a fleeting, golden era of the universe, a time when stars still shine and complex matter can exist. But this era is transient. All the achievements of humanity, all of our art, our science, our love and our loss, every civilization that has ever risen or will ever rise, will ultimately be erased by the relentless march of cosmic time. Our planet will be consumed by the sun in a few billion years. Our galaxy will merge with Andromeda, and in the unfathomably distant future, the last light in the universe will flicker and die. This perspective is simultaneously terrifying and awe-inspiring. It reveals our profound insignificance on the cosmic stage, yet it also highlights the incredible improbability and preciousness of our brief moment in the sun. We are a way for the cosmos to know itself, but that knowledge is destined to be lost in the endless dark. The universe's ultimate fate is the final, humbling truth, a reminder that all stories must end, and that the greatest drama of all is playing out on a stage so vast we can scarcely perceive it, heading toward a curtain call that will leave no one and nothing to remember it ever happened. And so our journey through the cosmic abyss reaches its end. We have navigated 25 profound terrors, each revealing a universe that is anything but the serene, twinkling tapestry it appears to be. From the silent, gravitational pull of the Great Attractor to the universe-shredding potential of a phantom energy Big Rip. From the invisible threat of vacuum decay to the silent, frozen wanderers we call rogue planets. We have confronted stellar zombies, pulsar death beams, and the chilling silence of the Fermi Paradox. We have seen how our own technology could ensnare us in a prison of our own making through the Kessler syndrome, and how the very laws of physics might be undone by a black hole's information paradox. We have even questioned the nature of our own reality within the simulation hypothesis and discovered the cosmic scar of the CMB cold spot. This is not a universe that is merely indifferent to us. It is a cosmos filled with active, existential threats, governed by forces of unimaginable power and scale that dwarf our petty human concerns. It is a realm of profound darkness, punctuated by brief, brilliant, and violent events, where the very concepts of time and space can become weapons against us. Yet, in the face of such overwhelming and terrifying truths, we are not left with mere despair. This knowledge, however frightening, is our greatest tool. It is the light we shine into the dark. To understand the destructive power of a solar superflare is to one day perhaps find a way to shield our civilization. To comprehend the distant danger of gamma-ray bursts is to appreciate the fragile, fortunate oasis our solar system provides. Even the far future fate of the cosmos, whether a heat death or a big rip, grants our present moment a searing, precious beauty. Our time here is brief, but it is our time to look up, to learn, to feel awe, and to wonder. The universe may be filled with horrors, but it is also filled with majesty, mystery, and the incredible phenomenon of a species that can strive to understand it all. Now we turn this over to you. After this tour of the universe's dark side, which of these 25 space horrors chilled you to your core the most? Was it the personal, psychological dread of quantum immortality, or the colossal, impersonal force of galactic cannibalism, the silent threat of a rogue black hole, or the explosive end of a neutron star merger? Let us know your thoughts in the comments below. We are truly fascinated to hear what captivates and terrifies you about the cosmos. If this journey into the unknown left you wanting to explore further, be sure to subscribe and hit the notification bell so you don't miss our next cosmic adventure. Remember, the universe is vast, dark, and filled with wonders and terrors beyond our imagination. But as long as we keep looking up, asking questions, and seeking knowledge, we carry a light with us into that dark. Thank you for watching.